Hello everyone, I'm Ramanpreet Singh Pahwa. I work in the Machine Intellection Department in iScholar A-Star, and today I'll be talking about 2D, 3D image segmentation, and then I'll discuss basically how image segmentation is done classically, how deep learning has impacted this field, what are the current state-of-the-art models that are being used for both 2D and 3D. I'll also discuss what modalities are used in 3D and how do you tackle different modalities in 3D differently. And I'll also at the end discuss some use cases in particularly related to AME domain and basically show some results and discuss some key things that we need to account for in terms of AME. Okay, so the agenda of this talk is I'll first introduce what image segmentation is. I'll talk about some important concepts that are part of image segmentation, such as dice score, IOU, pixel accuracy, and so on. I'll discuss various losses that are used in deep learning models to perform image segmentation. After that, I'll move on to 2D image segmentation and discuss some of the state-of-the-art models that are being used, sort of show some inspiration how these models were invented, and then show some results for those segmentation models. After that, we'll move on to 3D. I'll discuss 3D representations, terminologies, and metrics. And then I will discuss and show some results for 3D image segmentation. And at the end, we'll just go through some case studies where my group has applied 2D and 3D image segmentation for various problems that we have solved in iSquare. Okay, so where can image segmentation be helpful in terms of AME application? Um, Things like transportation. Maybe we have to detect some faulty walls in the train, or we have to detect some faulty train tracks, or maybe you have to find some graffiti on the trains. So that's where image segmentation along with object detection can be used. In terms of semiconductors, detecting various defects that may be present in both 2D and 3D, such as void detection, crack detection. Um, Rather than getting technical, some other defects such as solder extrusion, pad misalignment, and all that I'll discuss later in the slides. Also, robotics. So, uh, a robot that's a service robot that needs to deliver objects from point A to point B not only needs to perform object detection, but also may need some image segmentation as well to figure out certain details that object detection alone cannot provide. Okay, so let's start with the definition of image segmentation itself. Like, what do you mean by image segmentation? Essentially, this means that we're grouping pixels into meaningful or perceptually similar regions. So what that means is, so given a particular image, we want, let's say, the leaves background as one class, the foreground, the person, as one class. So once you obtain a binary mask, which basically separates the foreground from the background, you're able to basically use that mask. You can sort of multiply it with the image to essentially just get the person that's inside that image. Essentially, it's very similar to a classification problem. So, like Arul discussed in week one, how classification is done using CNNs. In those networks, you basically take in an image and you perform multi-layer CNNs, and your output at the end is essentially a class, right? Like can be if there are only two classes, your output would be like a binary output. If you have multiple classes, well, you'll have a vector output most likely. So over here, we are not outputting class one global class of the entire image. We essentially want that kind of output for each pixel. So if your image happens to be, let's say, 512 by 512, right, that's 250,000 pixels. So doing a similar classification like what you did for pure image classification problem would be highly intractable. So we need to come up with more efficient methods. And of course, we can use some additional information such as neighborhood information, local consistency, global consistency, and so on to make your work easier. So for example, um, the way one of the other ways that we can use segmentation, in fact, the way segmentation is being used is in your cameras. You have your portrait modules, right? So what it does is it will blur the background for you. So the way it's doing it is it identifies the location of the person, and then it will basically segment out the person's boundary, and then whatever the background is in the image, it will blur it using using a Gaussian blur or some other blur function. YouTube stories that are popping up now in your YouTube apps allows a person to basically record a short video with the with the selfie camera. So essentially what it's doing is something similar where it detects the person and the background, and then you're able to change it to a different background to create your YouTube stories. Your zoom functionality where you can have a virtual background exactly the same thing. Previously, the way segmentation was being used was to sort of group neighborhood pixels together and call them super pixels. So you would group anywhere between 4 by 4 pixels or even 16 by 16 pixels to kind of reduce the size of the image while maintaining um, the grouping consistency of the image itself to perform various image processing or various inference that was required for your modules. So essentially, how do you do that, right? Like so given a sample image, you can perform image classification exactly the way that Ardur discussed in previous week. On the other hand, you can do object detection, which is essentially locating perhaps a particular class in the scene, and then figuring out the bounding box that um, overlays on top of that object. And then you can perform object segmentation just in that bounding box. So essentially over here, this can be considered as object segmentation because you're finding the object first using localization detection, and then you're performing segmentation. If you're looking at an entire image and then you're performing segmentation for each pixel, that would be considered as image segmentation. This can be done directly, or this can be done after classifying the image. Maybe you classify this image as train. So when you do the segmentation, perhaps you use this extra knowledge that you know there's a train present inside. The features that look like a train and all, right? So you could group them together into one segment as a whole. So um, let me first just talk about different types of image segmentation we'll be looking at in terms of our discussion from here. There are three types of image segmentation. Binary segmentation, which is essentially given an image, we kind of just do a binary classification, whether that belongs to a foreground or a background. So in this case over here, these are train tracks. So this region over here is your foreground, the train track. Everything else is your background, which is your zero mask and a binary mask with zeros and ones. And then however, if you have multiple classes present in the image, you would call that as semantic segmentation. So what semantic segmentation means is you have multiple classes. So for each pixel, it's not just about foreground, background. You would say that well, there's pixels that are background, like they don't belong to any of the classes we're looking for. But if you identify something as quote unquote foreground, you also need to figure out what class that particular pixel belongs to. Is it pedestrian, cyclist, buildings, road, cars, and so on. And in the case of semantic segmentation, you basically all the cars will be labeled with the same label. You can go one step further and something called, and then you can perform instance segmentation. What that means is that for each instance of the same class, for example, cars, each car, if there are X number of cars present in the scene, you want to have X different labels for pixels for each of those X cars as well. So to sort of explain this a bit further, semantic segmentation, you label every pixel as belonging to a class, right? Like you partition an image into coherent parts, essentially. Like if you look over here, you have grass, you have ground, building, sky, tree, roads, bicycles, and so on. Um, So in terms of between binary and semantic segmentation, right? Like you're looking for multiple classes. So let's say in binary segmentation, you're only looking for, just along. So over here, you're looking for more than just one class. For instance segmentation, you go one step further than semantic. So in semantic segmentation, maybe you're just looking for table, you're looking for chairs, you're looking for, walls and windows, let's say. However, for instance segmentation, you would want to label all the chairs as different instances, like chair 1, chair 2, chair 3, person 1, person 2, tree 1, tree 2, and so on. So all the labels are instance aware as well, right? So like for example over here, um, you can think of it as binary segmentation or semantic segmentation, right? This one over here would be instance segmentation because each person is labeled separately, even though it's the same class as person. So what are some of the applications of image segmentation? I talked about some very basic ways of using image segmentation for background blurring, for YouTube stories, and Zoom virtual backgrounds and so on. But in terms of AME domain or BME domain, which is biomedical, like where is image segmentation actually used widely? So in medical images, we use image segmentation extensively to segment out organs and vessels, even some parts such as brains, livers, kidneys, lungs can be segmented out using image segmentation. And in particular, we it is widely also used to identify and basically segment out tumors that may be present in brains, kidneys, lungs, and there are various different data sets in 2D and 3D for tumor detection. You have BRATs for brain tumor segmentation, you have LITs for liver tumor segmentation, you have KITs for kidney tumor segmentation, and so on. Um, Most of these image segmentations required in medical imaging are usually 3D because you're dealing with 3D X-ray scans or CT scans, which are essentially like voxelized data that we'll look at when we get to 3D segmentation. Image segmentation is also widely used for autonomous driving. It's used for traffic, identifying traffic and road signs, your lane and road detection, even for some parts you might want to know the car that's going around in the road. Even for that, you can use object detection or image segmentation as well. In image segmentation is widely used in the semiconductor area. It is used for component detection, especially when it comes to 2D and 3D. You might use it for some buried components such as your TSVs. TSV stand for through silicon vias, your logic die or memory die that you use for chip stacking. You can use it for crack detection that may be present in the semiconductor components. Measuring the sizes of different components that are being fabricated. This can be done with image segmentation and post-processing using computer vision to measure in pixels how big or what is the shape of a certain component you're looking for. You can also use it for things like impurity detection. What if there's some dust that is present on top of the chip? We have used segmentation for that in our prior projects as well. And it, there are other areas as well where we're using it widely, such as robotics, aerial imaging, 2D, 3D metrology, image in painting, and so on. So now the question becomes, well, we can do image segmentation, but how do you define a good segmentation? Of course, there are metrics that we'll talk about that sort of numerically identify whether something is a good segmentation or not. But intuitively speaking, how do you know whether something is a good segmentation or not? So let's look at the image on the right side, and we are only looking for single class, i.e. binary segmentation. So this is the region that we are looking for in terms of foreground regions, right? So what would be a good segmentation over here? Of course, we would want sharp boundaries, right? And one way to do that could be, well, how about we look at intensity values, right? And maybe we can find some boundary decision that can give us reasonably good segmentation. But that will mean that the inside parts over here will have lots of background, which is not what we require, right? So we want sharp boundaries, but at the same time we want something consistent. So you want neighborhood consistency, you want sharp boundaries, you want something that's quick enough, and so on. Okay, so the goal over here would be fast, efficient, and accurate. You want it to be consistent across pixels as well as across multiple images. So if I give you another image, right, with a different data distribution for this kind of noise, you would still want to have similar segmentation for foreground, background. So intuitively, essentially, consistency is the key when it comes to segmentation, along with sharp boundaries. So now let's talk about metrics that are involved in image segmentation. There are various metrics you can use for image segmentation. Some of them will be similar to object detection, but some are indeed new and different that you do not see in object detection. So I would recommend you to keep to do listen to this part of the video, even if you have seen the object detection lecture. So the first one is pixel accuracy. Now, pixel accuracy, as the name suggests, is essentially how many pixels you got correct. So let's say in the person is your foreground that you're looking for, right? Everything else is background. So you can call them as negatives, and your kind of your foreground as your positives, right? So your accuracy would be this term over here. What does this stand for? True positive means correct foreground prediction for a foreground pixel, which essentially means this region over here. This is actually foreground, and we correctly identified this as foreground, right? Then false positive, as the name suggests, is the wrong foreground prediction of a background pixel. So this region over here, this is actually background, but our model, let's say, identified it as foreground. So this becomes a false positive. In AME terms or industrial terms, sometimes it is also called false alarms. Now you have false negatives. False essentially means that you identified something incorrectly, right? So the opposite of this would be false negatives, where you identified something as background, which was actually foreground. In semicon especially, this is called escapes. True negatives suggest, as the name suggests, is essentially current background that is identified, predicted correctly as, should be background over here, background pixel. So in a sense, if you had the perfect results, your false positive and false negative would be 0, right? And your accuracy would be 100%, because then this and this will be 0. So essentially you're just left with this term over here, which is 1. Now, There are two more metrics that are used very often even now, which is precision and recall. So what are they? The equation for precision is given by true positives, this region over here, divided by this region, true positives, plus false positives, which is this region. For recall, it's again true positives divided by the same region, true positives, plus false negatives, which is this region over here, right? So if I ask you which of these two is more important, uh, what would you think? I'll give you 30 seconds or a minute to think, then I'll answer the question. Okay, so as some of you might have guessed, well, there's no straight answer. Um, the best answer is that it depends, right? So uh, now let me explain how they're different. What happens to precision and what happens to recall as your model accuracy goes down. Your model accuracy will go down once you start getting more true negatives, false positives and false negatives, right? So your precision um, goes down as you get more number of false positives, which means that you identify more foreground pixels or foreground hits than they were, or in areas where there was no foreground. Your recall reduces when your false negatives increase, which means that you weren't able to identify the foreground where there was actually foreground, right? So usually this precision, usually the way you decide something is the foreground or not is based on a threshold that will come in the next one or two slides. So to increase your precision, you want to reduce your false positives. To increase your recall, you want to reduce false negatives. If you increase your, rather if you decrease your false positives, the way you would do that is you would want to be as accurate as possible about your decision. You only want to identify something as a foreground if you are damn sure that it is a foreground, right? You do not care how many of those foregrounds did you identify. If you're only sure about this region over here as foreground, that's it. You only identify this as foreground, right? So this would be true positives, right? Everything else would either be true negatives or false negatives, right? But this equation over here does not have false negatives in it. So your accuracy, or your precision rather, would be 1, while your accuracy might be very low, right? Same thing with recall. I mean, same concept with recall, but the opposite way. To get really high recall, you want as low false negatives as possible. Well, one way to do that would be, well, everything in the image is a foreground, right? So if everything in the image is the foreground, well, you did identify everything over here correctly, right? So your true positives is basically this entire person, and everything else over here, right, is a false positive, right? But in recall, false positive doesn't exist. So your recall would be 1, but your precision will be really low. And similarly for precision, while your FP might be really, really low, your false negatives will be really, really high, and hence your recall will be low for high precision. So essentially these two are in some sense negatively correlated with each other. So which one is more important? Well, it depends, right? If detecting your foreground is very critical for you, you want to detect as much foreground as possible, you would want high recall. However, if you don't want to detect too much of the foreground because it requires more estimates or more other quality checks, then well, maybe you can escape. You can escape with reasonable precision, but maybe you want a higher recall. So I'll give you a couple of examples, right? So some of the projects we had to detect cracks in the images, be it semiconductor cracks or just wall cracks in general, right? Detecting a wall crack is important, right? But at the same time, it's not very expensive if you miss one. So while we would want as high precision and recall as possible, um, what the customer wanted was a good enough um, uh, a good enough your precision, right? With high recall. Right. So in this example over here, this is a crack present in a wall. So in this kind of problem setting, the customer may want us to be really sure about what we are detecting as a crack to be actually a crack. Um, they don't want the quality assurance person to basically look at so many images that may not contain cracks at all, and it's not really very important. If you may miss a couple of cracks here and there, it's fine, but what they really want is whatever images we are giving them do indeed contain cracks. So in that problem setting, we would want a high precision, or rather we want as high precision as possible with a reasonably high recall. On the other hand, if you look at the image on the left, this is a semiconductor image, and cracks present in semiconductor components is very, very bad for the yield. Essentially, if one of the components contains a crack, chances are that some other components in the same batch may contain cracks as well. And this can lead to product recall, it can lead to, things like your battery exploding and so on. So it's very critical that you detect any defects that may be present over here. So in this case, you would want very high recall. In fact, you do not want any escapes, right? So if you do not want any escapes, you want false negative to be 0, which would mean that you want a recall of as close as possible to 1, while maintaining a high enough precision that you just don't output every image as maybe it contains a crack, right? So that's how you decide, kind of try to find a delicate balance between precision and recall. Okay, so now precision and recall curve is a good way to evaluate the performance of an object detector, as the confidence is changed by plotting a curve for each object class. An object detector of a particular class is considered good if its precision stays high as recall increases, right? And which means that if you vary the confidence threshold, the precision and recall will still be high, that you want it to be as high as possible around this region. Another way to um, another way to identify a good object detector is to look for a detector that can identify only relevant objects, right? So a lot of times this would also be used for object detection, right? For both segmentation and object detection, you basically want something that gives you very high precision and very high recall. So in AME domain, we want as few escapes as possible. So you kind of want to stay closer to this region over here, right? But ideally, you want your precision to be as high as possible as well. So, however, let's say generally speaking, if you come up with an algorithm, right, and you plot your precision recall curve, and your precision recall curve looks like this, your baseline method that you're comparing against has a precision recall curve like this. How do you identify which algorithm works better, or which model works better? In some cases, your baseline method gives you better results. In some cases, your method gives you better results, right? That's where you perform something called area under the curve, AUC. So essentially, you just sum up the area that's underneath this region over here for both the curves, and we call that as average precision. So if your average precision is higher than the baseline method, then you can confidently say that your method indeed outperforms the baseline method. Other metrics that we're using, I've been talking about this a lot, but I kind of wanted to give an intuitive understanding before we got started over here. This is called intersection over union. So intersection over union is essentially, as the name suggests, area of overlap divided by the area of union. If you recall from what true positives, false negatives, and true negatives were, the intersection would be your true positives, right? Things that you were not able to detect correctly are your false negatives, and things that you thought were foreground but were not are called false positives, right? And area and the union would be just the intersection of the two proposed, the ground truth region and your proposed foreground region. This can also be written down as sum of the areas of the ground truth and yours minus this intersection region. Dice, on the other hand, would is similar. Basically, it's two times the intersection, i.e., the true positives, and at the bottom, you're basically summing them up, which is essentially you do not have the minus true positives over here, which would lead to this area of union over here. So these two are, they look very similar, right? How come there are two different metrics over here? And um, which one is normally used in image segmentation, right? So this question comes up very often. And yes, indeed, these two are actually highly correlated. And in fact, not only are they correlated, they are deterministic. What I mean by that is that your intersection over union will always lie in between the value for dice, between half of that value and the full value. If you get the perfect results, right, like your intersection is absolutely uh, perfect, then your IOU will be 1, your dice will be 1, right? However, if there is no intersection at all, right, then in this case over here, right, this will be 0, this will be 0. And IU can be written down as dice divided by 2 minus dice. And similarly, you can write dice as equation in terms of IU. So uh, which one do you use? Usually speaking, we use IOU for object detection and we use dice for image segmentation. IOU score normally measures something closer to the worst case performance. So think of it as your L1 norm. Your dice score tends to measure something closer to the average performance. So think of it as your L2 norm. And there's one additional thing I would like to mention is if I let me see if I can go back. No, looks like I can't. So if you remember your equations right over here, what happens if your you had an image, let's say an image of those walls where you're trying to detect a crack, right? And indeed, there was an image without any crack, even the ground truth, like there was absolutely no crack there. So your foreground was 0, right? And you also correctly identified that there is no crack in that image. That means your proposed detection or your proposed foreground is also 0. You kind of run into this issue of 0 divided by 0 in both the cases, right? And you want to avoid that. So the way you avoid that is normally you add a denominator term for both dice as well as IOU calculation. That denominator term, you would think that if you've done enough, if you have handled this kind of numerical instability enough number of times, intuitively you would think that value would be something like epsilon 10 to the minus 6 or something. Just a very small number, so it doesn't impact the results over here. It doesn't impact the true IOU and dice value. However, what scientists have found empirically is that it's not epsilon that makes it numerically like that makes it converge faster. What really helps is just adding a value, a unit, one value. So you just basically add one on both the sides for IU and dice for denominator, and you're good to go. So now let's talk about loss function. So this part, I may speed up a little because it's very similar to the metrics. One of the most common loss functions that is used for image segmentation is your dice loss, which is exactly similar to your dice coefficient that we used before. Another one is intersection over union, and we've already talked about these. These are usually used for kind of, let's say, balanced data sets that have reasonable enough foreground and background. Now, what happens if you have really highly imbalanced data sets? So for imbalanced data sets, you would use either something called focal loss, which originated out of a RetinaNet paper, a very highly cited paper. And what it does is it changes the cross entropy loss shape such that the loss assigned to well-classified examples is downweighted. What really that means is that if you look at the graph over here, the examples that are classified correctly, right, um, they will be weighted much lower than the images with the high loss, right, where they were classified incorrectly over here. So that way, you're kind of like forcing your model to improve on the wrong detections, while kind of ignoring the consistently right detections completely as part of your overall score. Another way would be to use weighted cross entropy. So essentially, classes with less foreground, let's say, right? You would assign it a higher weight, so you can kind of get equivalent balance between different classes. And another way to account for imbalanced data set would be to use data augmentation heavily. Perhaps you employ a lot of data augmentation to create data for the imbalanced classes, or rather the less frequent classes, so as to create this data set which is augmented and contains somewhat balanced number of classes for each balanced number of examples for each number of classes we're looking for. So before we delve into the deep learning based segmentation models, I would like to just quickly go through some of the classical methods just to understand where we're coming from. And it will also kind of explain how some of the segmentation models currently originated from. So the very basic way of doing segmentation would be k-means, watershed algorithm, mean shift, and some of its variants. So in k-means, what you would do is you would basically pick a few number of clusters that you're looking for. So let's say in this example over here, looking for 3 clusters, right? Green, or rather for green, red, pink, and blue. So you would have to specify how many clusters you're looking for, and then you would randomly assign center to 4 of these pixels as your center points for these 4 clusters. And then you will start doing some kind of distance computation. It could be based on your intensity information. It could be a combination of intensity and pixel distance from the center, and so on, right? Based on what kind of segmentation you're looking for. And eventually you will keep iterating. So once you identify these distances, you basically figure out which the pixel closest to which center. You will assign that pixel to that particular cluster, and then you will compute these distances again. And then for each pixel, you would look at which cluster it belongs to as the closest distance, and then you would reassign it to that particular cluster. And you'll keep iterating over until there are no more changes left. So that's how k-means works. Um, so algorithms like these have either two types of approaches. Either their bottom-up approach, which means that you group tokens with similar features, right? Like over here, you basically have features like your horses is like a animal. You have grass, you have trees, and so on. Depending upon how many clusters you pick, you can either get over segmentation or severe under segmentation. Then you have your top-down approach, where you group tokens that likely belong to the same object. So over here, you're looking for like kind of object-based segmentation. So you're looking for like this horse. So anything inside over here would be classified pixel-wise as this particular object. And then you have some other methods such as graph-based methods, heuristic methods, which kind of look at splitting and merging the regions, region growing, and energy-based methods. So a lot of these methods were computationally very, very expensive. A lot of them ended up doing super pixels as well because you just didn't have enough power to do the segmentation for each pixel. So there was a big gap here in terms of accuracy. One sec. Okay, so now one way to kind of avoid some of these pitfalls that come from classical techniques would be like, how about we just take one small part of the image, run a convolutional network like Arul described, and then we can perhaps classify each pixel as foreground background if you're doing binary segmentation, right? So let's say in this case we're looking for cars, and everything else is background. So for each of these windows, you will run a CNN, and then you can classify um, the pixels to be either foreground or background. And there are lots of issues with such a basic idea. Um, First of all, you're not looking for global features, right? Like you're just looking for something in that particular image, a particular crop of that image. It's very time consuming, very memory intensive. You have to go through millions of these bounding boxes, right? And it's kind of a fixed bounding box, so you can't really use neighborhood information that could really assist you in terms of finding correct edges or finding sharp edges and so on. So, um, as I mentioned, the way you would do that is you basically divide the image into multiple sections. You can extract that particular patch. You can kind of like how you run a classification algorithm, you could run a segmentation algorithm for that, right? However, it's extremely inefficient and time consuming, very similar to how we can do object detection for these windows. Um, as I mentioned, no neighborhood consistency will be used here, and you cannot really share features between overlapping patches. So in this part over here, there's a small patch that is overlapping, right? But you're running CNNs on them individually, separately, so you're not really using any features that were extracted from the blue region CNN versus the pink region CNN. So now we want to make it more efficient, and we want to make it more accurate, and we want to kind of use local consistency, global consistency, and so on. So there are a lot of areas where we can improve our basic idea of segmentation. So the first thing you could do is you can run fully convolutional networks. So given an image, a color image, so 3 by H by W, so height times width, and 3 is the number of color channels. You could run convolutional networks, with D filters, and then you can basically have multiple of these convolutional layers, and at the end, you basically predict a binary image that is of the same size as the input image, with a label for each pixel for number of classes you have. This makes the results much more efficient compared to, let's say, a sliding window, right? However, it's still very computation intensive because let's say if you're looking for a 1,000 by 1,000 image, right? Like the number of parameters involved over here to do this fully convolutional network would be really, really huge. So we want to avoid this whole exploding in terms of parameters needed to do convolutions. So the scientists came up with an idea for encoder decoder. So what you do over here is, given the same input image, you're kind of like downsizing. So you go from H times W to H by 2 times W by 2, then H by 4 times W by 4, and then you kind of have like a bridge, and then you have your decoder where you are upsampling the size again. you want to maintain the same amount of information here. I believe Arul also explained it. So what you do is your number of filters will basically increase. You can see this kind of the depth. This is basically your number of filters. So initially, because you're using a high resolution, you have D1 number of filters. When you downsample it, you basically increase the number of filters over here, usually double, um, to basically maintain the same amount of information over here. Similarly, over here, your D3 would be uh, about double of D2, and at the end, you basically have kind of your fully convolution blocks to get the final prediction. So over here, you can maintain almost the same accuracy, but you can severely reduce the number of parameters needed to create this sort of a CNN block. So based on these ideas, there are a lot of segmentation networks, both in 2D and 3D. So in 2D, the major segmentation networks that you could look at are UNets. These are binary networks, more or less state of the art. You have your dense nets, which were designed for classification, but they've been extended to do segmentation as well. You have Deep Lab, you have Segnet, as the name suggests, is for segmentation. You have Mascar CNN that can also do segmentation. In 3D, you basically have things like 3D unit, you have NN unit, that stands for no new unit, a very, very interesting paper. You have Chi-CNN, which is what we came up with, point nets for RGBT data, and some hybrid networks that basically use combination of 2D and 3D information. So let's start with units. As the name suggests, the reason why it's called unit is because the structure looks like a U, as you can see on the right side. Very similar to like the encoder decoder idea. Essentially, you start with original resolution of the image. If your image happens to be, let's say, 572 by 572, which is what they used. If you have a bigger image, you would probably downsample it to this resolution before you can feed it in for training. And then you basically have these convolutions, 3 by 3 convolutions with active with ReLU, and you do it twice per layer, right? And then you would do your max pooling, your downsampling, and then again you would do basically convolutions, downsampling, and you do it 4 times. This part over here is usually called bridge. Essentially, you're just doing convolutions again, and over here you're basically doing your interpolations or up convolutions. So the difference between encoder and unit is essentially these arrows that you see over here. They are called skip connections. So the problem with dense, those encoder decoder idea is that as you go down, even though you try to increase the number of filters, as I already mentioned, the resolution of the image reduces. So you may not be able to look at some of the very fine features that are needed for detection, especially for things like crack detection and all. So what you want is you want to kind of get the global consistency that you get from downsampling and upsampling in an encoder decoder, but at the same time you want to retain the fine-grained information that is present at the upper layers. So for that, what you do is you basically carry over the output from these convolutions to the decoder side, and you concatenate it together to perform your convolutions in the decoder component. So, and this paper basically revolutionized binary segmentation. It has, I believe, more than 1,000 citations. It was mainly designed for medical scans to find tumors in lungs and brains for your LITS and BRATS dataset. There's so many variants that came out after UNIT, and we'll talk about a couple of them. And it's built on essentially, top of fully convolution neural networks, um, U-shaped. So the novelty over here that I talked about are these skip connections or shortcut connections, they call it. Um, and as I explained, downsampling will result in loss of final information. Concatenation of this fully sampled data and the upsample data that you're getting from over here essentially keeps the number of parameters in check whilst having access to this finer information that you would lose if you were using an encoder decoder kind of architecture. Uh, so units gave you decent results, but there were some issues, especially with sort of really fine-grained information, and um, essentially, like training the network was a bit um, difficult. Like it wouldn't converge very well, and so on. So what research community did is they tried to basically combine the idea of REST nets with units. So if you sort of zoom into what this convolution block looks like over here, essentially you had the input being fed into a 3 by 3 convolution followed by ReLU activation, and then again similarly a 3 by 3 convolution followed by ReLU activation. So essentially this is what was happening in this region over here. And imagine basically going all the way over here with convolutions and ReLU. So at the end of when you got to this bridge area, it is you basically had difficulty in training and getting the network to converge in a reasonable time. So ResNet, on the other hand, basically came up at that time came up with this really brilliant idea of adding a identity connection. So this helped in making the network training reasonably fast, and there were absolutely no additional parameters to train because all you're adding is just this identity um, connection over here. On top of that, there was no normalization in the original unit paper. So the community also added a batch normalization. So instead of having sort of a con relu, now we had batch normalization, relu con, batch normalization, relu convolution as your main block. But along with the ResNet idea, we basically had this identity mapping as well to get the output for each layer. This significantly not only improved the results because it also eased the training of these very deep unit networks. Another way people improved 2D unit is by using the inception module. Um, so essentially, instead of just upsampling using your up convolution, scientists introduced the inception module. The great thing about inception module was that it performs multi-scale feature extraction over here. So it significantly improved the results using this inception module for really tiny uh, tumoral structures that were present in the biomedical field. And the paper basically showed that the results, the improvement was significant for, I believe they had, glioma and some intratumoral structures. So you can see from units to the inception-based unit, the overall um, DICE score, DSE over here stands for DICE score, improved for almost every category for WT, TC, and ET stands for whole tumor, tumor core, and enhanced tumor. If you look at Brad's dataset, you will see these three segmentation regions that are needed. And when I show our work on this dataset, you will also see this in the later slides. Okay, so now a brief intro into RCNN. So one of the papers I'm going to talk about is mask RCNN. But before I can get into mask RCNN, I need to show how the motivation behind mask RCNN architecture. So as you might have seen in the object detection lecture, uh, one of the major breakthroughs were in object detection were RCNNs up to faster RCNN. So I didn't go into too much detail there. So if you are still interested to know more about them, I would pay attention to the next few slides over here. So in RCNN, which was designed for object detection, not segmentation, the way it's done is essentially it's a two-step object detection method. So you have something called object proposals, which is basically some region inside the image where the algorithm thinks there's something highly likely that there's an object there. You don't know what object it is or whether it even contains an object or not. You just think there's a high probability that it contains an object. So this is done using selective search algorithm, which actually does like kind of segmentation. So based on the segmentations, you come up with these 2000 object proposals. These 2000 object proposals are then kind of resized to a static kind of bounding box, and it goes through a convolutional neural network to perform feature extraction. And on these features, you basically perform classification and bounding box regression. So essentially identify what class it is and what is the size of the bounding box for that. This part was very slow, right? In this finding these 2000 regions using selective search was very slow, and overall, because of the way we are doing this warping and all, the results may not be very accurate, especially for odd-looking objects or odd-sized objects. So what fast RCNN paper did was they still use the basic idea of using selective search for finding the 2000 region proposals. However, the CNN basically goes through the image first, as you can see over here, to extract the features from the image itself. Let's call them feature maps over here. Then your ROIs are basically obtained on these feature maps over here, and then you basically perform your fully connection layers based uh, estimation. I mean, this is basically your model over here that you're training, and then you perform your bounding box regression and classification simultaneously. So in FastStar CNN, basically what we did was we brought the CNN directly in front of the image to extract feature maps, and then basically these feature maps are shared for the ROI pooling component, and ROI pooling is performed on the proposal, right? In faster RCNN, which significantly made it faster and more accurate, we got rid of this selective search component for the finding these object proposals. So rather than using a static method, selective search, which could not be trained. So let's say if you missed some image, some object detection, some object inside these region proposals, you were never ever gonna do improve the regression or improve your classification on that, because it never came up in these proposals. So basically region proposal network also became trainable now. So the input image again goes through the CNN for feature extraction to generate your feature maps. Now the region proposal network, this RPN, is used to estimate the object proposals on these feature maps itself. And then similar to your fast RCN, RO pooling is performed on the proposal that goes through the network at the end. So this part is exactly the same, except that basically now you have this extra region proposal network. So now what mask RCNN did was add one more module to this to this faster RCNN concept, which is they basically added a mask branch over here. So the architecture, other than this mask branch, is exactly the same as your faster RCNN. This mask branch is basically used to generate binary masks for this instance segmentation that I believe should come up now. Yeah. So as we saw before, basically this is the new part over here. So what's happening over here is, on one side, you're basically detecting the bounding box, and you're detecting the class of the object that's present in that bounding box. And on this side, you're essentially resizing or getting a convolution output of 14 by 14 by 80 size, which basically is your mask output for that particular data set. So for ResNet, as you might know, your output is essentially 7 by 7 by 2048. So you can apply one by one filters on it to average it out for each of those 7 by 7 by 248 convolution block over here, and then you can perform your estimation for your class and the bounding box output based on that layer. So in this case over here, you basically have a separate head that will output 14 by 14 by 256, followed by another convolution block that outputs the final mask, which is 14 by 14 by 80. So the loss that is used over here is a combination of three losses. You have your classification loss, right? You have your bounding box, not binary, sorry, bounding box regression loss, and you have your uh, loss for the mask itself, right? So the reason why I didn't mention why this is 14 by 14 by 80. 80 essentially is the number of classes that you're looking for, and M over here stands for basically the resolution of the prediction mask, which is 14 by 14. Overall, this can be extended to even do pose estimation, and the results are actually really, really good. So the network as a whole, this part over here, FastRA CNN does a great job of finding all the objects that are in the scene, and then this head over here for the mask branch is able to segment that region for you. So that's why when you look at the outputs from mask incident, you will tend to see these bounding boxes. So this is the bounding box that was estimated. And inside this bounding box, you're basically getting the segmentation output for the class that's inside that region. So the results, as I mentioned, are very good, and it can be even extended to do pose estimation for objects that are inside this bounding box. So a very cool paper. The original DenseNet was designed for classification. Um, it's a very popular paper with more than 14,000 citations. And the highlights for that paper were that it introduced parameter efficiency while maintaining deep supervision. And the way it did that was by basically using reusing the feature space. Okay, so now let me show basically how DenseNet paper uh, worked around some of the limitations of CNNs to get really good results while maintaining parameter efficiency. So in your standard convolution network over here, essentially given a, let's say, RGB image, you're going to apply K filters to the image. Let's say if it's the same size convolution, so you're going to get K times M by N, let's say, size, and you apply filters again and on, and keep doing that until the very end. The number of parameters over here would be huge because you essentially have these large number of filters for convolution at each layer. The way ResNet worked was while maintaining the same number of parameters, it introduced these skip connections or identity connections rather. So this way you could avoid exploding gradient or vanishing gradient problems. In essence, you're also carrying the information from the previous layer to the output of the current layer if needed be. DenseNet went one step further. So not only are you kind of sharing this information or you're obtaining that information from the previous layer, you're obtaining information from all the previous layers. So a connection over here, like an output over here, is basically getting information from all the previous three layers over here. In ResNet, you're basically adding the output from the previous layer in essentially called the identity mapping. Over here, you're not adding, you're actually concatenating. So there is a sort of a growth per layer. So let's say if you have K channels per layer, right? K channels per layer. Since you're concatenating, over here, let's say you have K, and over here you will have the output K as well as the concatenation from here, right? So this will be 2K. And then over here, you'll be having 2K from here, right? And then you'll have this one over here, which would be 2K, so and so on. So the way this would work is, as you can see over here, so this is an animation for the sort of growth per channel. So initially you start with X naught number of channels. After one convolution, you have X1 and X naught together as concatenations. And in the next one, you have x2, which is output from here, and then x1 and x0 as well. And it will grow in this fashion. So now, to kind of keep this thing reasonably to a reasonable size, what you do is you essentially run a one-by-one convolution in between to keep it in check. So let's say you have after your x3 over here, you have L times k channels, right? With after L layers, you would run your batch. You would do batch normalization, ReLU, and then you would have a one-by-one convolution. The output over here would be 4 by k, total number of channels, instead of L by k now. And then again you would do BN, ReLU, and then 3 by 3 convolution to get your final output X4, which has only K channels now. So this is how you basically go from L by K channels to the K channels as your output for each major convolution block over here. So this allows strong gradient flow as well as parameter and computational efficiency, because you're keeping these number of parameters in check while having dense connections across these different blocks. So these major component is called dense block in the paper. So you have 3 of them according to this image. And they looked at the results on the CFAR 100 dataset. The results show significant improvement without data augmentation, which is on the right side over here. So over here, the y-axis is your total error, so the lower is better. So ResNet at that time, if you looked at they looked at two different ResNet with 110 layers, which had 1.7 million parameters, and ResNet 1001, which had 10 million parameters. So of course, with enough training, the deeper network ResNet 101, 1001, sorry, gave us lower error. But if you look at the DenseNet, which only had 100 layers with 0.8 million parameters, there was a very, very significant reduction in the total error, and even lower than the previous state of the art at that time. And DenseNet with 250 layers had 15.3 million parameters and gave the best results. So even with data augmentation, DenseNet still outperformed ResNet, but you could see that with augmentation, your ResNet 1001 was able to get similar to your DenseNet 100, even though it had like 10 times more number of parameters. So, but over here, we want to do segmentation, right? So the way scientists extended this paper was the feature maps that were created by the previous dense block were upsampled to keep the computation and the number of parameters in check. The input of a dense block was not concatenated with its output like how it's done in DenseNet, in those dense blocks that I talked about. So instead, you basically had these just two dense blocks over here, right, with these skip connections that you saw in unit as well, which is very, very critical now that for most of the segmentation architectures. You had these transition downs, which essentially involved batch normalization, ReLU, one-by-one convolution with dropout and max pooling. So essentially, there was a reduction in the size of each, the dimension of each filter over here. And your layer over here was very similar. So essentially, your layer is a batch normalization ReLU 3 by 3 con with a dropout of with 0.2 parameter. And your transition up is essentially your upsampling component over here. So they use 3 by 3 transposed convolution with the stride equals to 2. So these are some of the results that were obtained using DenseNet, and you can see very accurate segmentation and clean segmentation as well. And I would like to say that at that time, one of the best segmentations that you can get in multi-class setting. And similar to unit, as I mentioned, like SIP connections are very critical to obtain, to keep the number of parameters in check and be able to get those small segmentation outputs accurately. So now let's talk about 3D segmentation networks. But before we can talk about that, we need to understand what data we are looking at. So in 2D, you basically have this grid of pixels, size, let's say m by n, and each pixel essentially contains the intensity information. However, things are very different in 3D. You just don't have kind of one kind of representation. You can have very different types of representations. If you look at non-Euclidean space, you can have point clouds. So essentially, each point in the space will have an XYZ coordinate, but there's no uniformity over here. It's based on how dense the object is or how many points you were able to capture on the object you're looking at, and so on. In terms of graphics, the rendering is done using lots of different graphs and meshes. So 3D data can also be represented in terms of these parameters. In terms of Euclidean structured data, you can look at RGBD data, which contains your color image as well as the depth image, mainly from things like Kinect. And then you can have volumetric data, which is essentially kind of a 3D cuboid that is divided into multiple, let's say, vertical planes, with each plane essentially of a certain depth, right? So let's say if you have a area or a volumetric area that is 10 by 10 by 10 meters, let's say, you could potentially divide it into 100 vertical planes, with each plane being 10 centimeters, right? So any point that's within those 10 centimeters gets assigned to that particular plane in that particular location. If you have more than one point, then you have to decide how you're going to work with that, right? And if you have no points over there, then that feature space may remain empty as well, like over here. And then you have multi-view rendering. So you basically are looking at the data or the object or the scene from multiple views, with either multiple cameras or a camera that moves around the object. I believe Shongwei will be talking about this a lot more in his talk later. So now let's talk about voxels. Essentially, voxels stand for volumetric pixels or volume elements. In 2D, you basically have pixels, right? So you have an image and it's divided into a uniform grid, and each of these 2D regions basically contains intensity information. Could be either grayscale information or could be RGB, like three color channel information. And you could extend this idea to 3D, where you have your feature space, right? And then you divide them into sort of a cube-like region. So each of these small chunks basically contain volumetric information of a certain sized cube, let's say 1 unit by 1 unit by 1 unit. So each of these voxels can be defined by a 3D coordinate, and which is essentially the location, right, in the scene. And it might also contain some color information, right, like what's present inside, is what point lies in this voxel, what is it intensity information. So voxels can, as I mentioned before, voxel can contain multiple scalar values, right? So if there are more than, if there's only one point lying inside this voxel, you could represent that voxel with that point's location, intensity information, right? However, let's say if there are 100 points lying inside, you're looking at something really dense in nature. So uh, how would you represent those 100 points inside this voxel? One way to that would be you just average out all the RGB information in that region, or you could store the statistical information, which is the mean and the variance, or you could just take the maximum value. So depending upon your application, there are multiple ways to represent this data. This kind of data representation is used extensively in especially two major fields: your 3D semicon data, as well as your biomedical data, where they use CT scans or ultrasound machines. Um, the way we would identify these different planes is sort of originates from biomedical field. So the three planes are your frontal planes, your sagittal planes, and your transverse planes. So essentially your frontal plane over here is looking at the person from the front. Kind of your top view is called transverse plane, and your cross section is your sagittal plane. So now, similar to how we did things in 2D, you could perform your convolutions in 3D now. But however, instead of using a 2D filter, you would be using a 3D filter now. So essentially, inside your voxelized data, you introduce a 3D filter, and you go through the entire input with this 3D convolution, with this three-dimensional kernel, and you get one scalar output. So this is how you would perform 3D CNN on 3D data representation. So now that we understand how voxelized data looks like, and what are some of the ways of representing data in voxels, now let's analyze some of the segmentation networks that work very well in this voxelized data. To no one's surprise, one of the best networks for 3D in this voxelized data representation are 3D units. Very similar to 2D. Essentially, you're just extending the 2D unit idea to 3D, where you basically have 3D CNNs now. And instead of using downsampling 4 times with like 4 layers, you only have 3, because the number of parameters now is a lot higher. So to keep the number of parameters in check, we don't downsample 4 times. Instead, we just do it 3 times. And your output would be basically, your input is n by m by d, where d is basically your depth for your 3D scan now, and your output would be n by m, a binary segmentation mask. Sorry, n by m by d, binary segmentation mask for the entire image. So to expand a bit more on what the 3D unit does compared to 2D unit, in the encoder itself, like you had 3 by 3 convolutions in your 2D units, now we have 3 by 3 by 3 convolutions. The original paper did not have batch normalization in 3D units, of course, because this came out later, after scientists discovered how batch normalization improved results for 2D units. They introduced batch normalization in the baseline 3D unit as well. And of course, going from 2D to 3D, your max pooling instead of 2 by 2 is 2 times 2 times 2 now for each dimension. Similarly, for your decoder, your each layer consists of up convolutions of stride 2 by 2 by 2 now instead of 2 by 2 for 2D. And you have again 3 by 3 by 3 convolutions followed by batch normalization and ReLU. Your shortcut connections over here, essentially you retain the same resolution, and you're just doing 3D CNN instead of your 2D convolutions over here, and nothing more. So nothing special about that, right? And the results are reasonably very good. And again, that paper has, I believe, more than 3,000 or 5,000 citations. NN unit, a very, very interesting paper, came out, I believe, in 2017 by Fabian. Um, the the name NN unit stands for no new unit. So as you saw in residual unit paper, the inception unit paper, scientists were coming up with really different ways in overcoming the limitation of the baseline unit. Um, what And of course the baseline 3D unit already accounted for some of those improvements where they introduced batch normalization and so on. Um, so what Fabian's group did was they said, okay, well, we have these two or three great 3D based units. Instead of adding some kind of heuristic improvements to those units, how let's explore what is the best output we can get from these units if we are able to automate certain things such as hyperparameter tuning and so on. And they realized that most of the improvement that they got um, was from things outside the architecture. How do you find your training data? How do you set your hyperparameters, right? What kind of ensemble network you use? Do you want to do your training and inference in 3D and 2D? So these are some of the things that NN unit paper did. So they found that more important than the new architecture was fine-tuning these hyperparameters. They pre-process the data by cropping, resampling, normalization. For training, they use five-fold cross-validation, and the loss was cross entropy plus dice loss that we've looked at before. They use some pre-selected augmentations. They even explored what augmentations work for the given data set. What are the best augmentations for them, rather than just using off-the-shelf augmentations. For post-processing, they use connected components. So if you do, let's say, segmentation in 2D, so you're getting per slice segmentations, right? Then you can sort of look at the neighborhoods to see whether you miss some segmentation. Or let's say if you're looking for vessels inside your 3D segmentation, and a couple of voxels where it's not connected, right? If you're looking for vessels, chances are, this just doesn't stop in the middle of the image. So it should be continuous segmentation. So this is how they improve the results further in the post-processing step. And they combine two or three networks together as part of ensemble. So they even explore whether they should just use one network or a weighted combination of multiple networks to get the best results as possible. Um, One of our in-house developed network is based on anisotropic CNNs. So it's a very deep network where we essentially try to share the weights across multiple of these layers. So each one of these blocks over here refers to 3 by 3 by 1 convolution, batch normalization, and your ReLU activations. And then you basically have your 1 by 1 by 3 convolutions over here as your output channel. And this step over here basically just means that it's a residual block with a certain dilation. So as you can see, in some sense it's like your dense nets, but we are also want to make sure that some kind of information is shared across two different phases of this architecture. So the couple of different networks we came up with were saliency map feedback network, SMFN for short, um, and which gave us really good results. So one thing we used in addition to that was that um, the tumors we are looking for are strictly inside the previous segmentation. So first of all, you look for the brain, then you look for whole tumor, you look for enhanced tumor, and then look for a tumor core. So each one of them is strictly inside the other. So this part was used as well as part of our architecture building. So over here we show our results using our two different networks, which are the multi-scale feature network as well as the saliency map feature network. And you can see that the baseline method has kind of false alarms, right? While in our case we are able to improve those significantly. And so for us, the whole tumor results were much better, and for tumor core also reasonably improvement over the baseline method over here.
Now, another network I would like to discuss is the PointNet network. This PointNet network is widely used, one of its variants is widely used also for 3D segmentation on RGBD or LiDAR data. Um, Conceptually similar to how the other segmentation networks are, there's a lot of data sharing. You basically are um, going from n by 3 matrix because you're only looking at the XYZ component over here. So for endpoints, each of these points have three information, the 3D location. So this is mapped into n by 64 and followed by n by 1024. And the local features that are obtained from over here, they are shared and concatenated with the global features, similar to how the unit network did its segmentation. So now, to sort of come to the closing of segmentation, 3D segmentation, these are some of the metrics that I use for 3D segmentation. We have talked about DICE, also called F1 measure. Jagged index over here stands for your intersection over union. We also talked about this. Your true positive rate, TPR, is essentially your recall, which is also called sensitivity. Your true negative rate is called your specificity, right? Your false positive rate, which you talked about as fallout, right, is 1 minus specificity, and so on, right? So the the ones that we talked about are, we can see that these are some of the major metrics that are implemented, right? So a lot of these we have already talked about over here. We also talked about your average distance, area under ROC curve, right? Some of the ones that are uh, also useful, especially in 3D, are your volumetric, volumetric similarity. In a sense, like it's trying to look for not just the overall intersection, your volume should be similar as well. And then you can have some shape-based metrics as well to make sure that your shape also resembles closely to the ground truth. So now let's take a look at some of the actual works in segmentation that our group has looked at, um, where we use both 2D and 3D segmentation for doing certain, achieving certain goals. So one of the projects we had was to do valve inspection in the SMRT dataset or the real dataset. So these images were taken from a high-speed camera of the sides of the train. And essentially, we're looking for these train balls. Um, the data set was very small. We only had 73 total images, out of which 42 walls were faulty. The resolution of each image is 1024 by 1400. So now, how do you define a faulty wall versus a normal wall? Uh, the way a normal, or rather a faulty wall is decided, is that if you look at the handle, the long handle and the wall body should have more than kind of a 90-degree angle between them. So in this case over here, your wall handle looks like this. So this part over here, right, should be looking up um, over here. So if it's below with a certain tilt, which is what you see over here, then this is a faulty wall. Now, if we had thousands of images of these label images for these, we could run a ResNet and we would get reasonably good results. Of course, we can use augmentations, but we can see that with such a limited data set, overfitting is highly likely to happen with ResNet 7. So now, what we instead did was we performed two-step segmentation followed by a post-processing step which did fault detection using a computer vision module. As the images are 1024 by 1400, you cannot perform even baseline unit segmentation on these before your GPUs at that time run out of memory. So, however, these walls are very small in size, right? So you would like to basically figure out this region of interest first and then perform segmentation in this region. And there are two ways to do that. One would be you basically train an object detection model to find this object, and then you can run segmentation on that area. Or if you're already learning a segmentation module, you could just kind of reuse that. And this is what we do over here. We basically have the same architecture. However, we train it for as a part of low resolution segmentation module as a high resolution segmentation module. So we would we would take the high resolution image, which is your 1024 by 1400 image. You downsample it to 25 by 256, and we have this low resolution unit segmentation module, which we train to basically identify where the valve is in the scene. This is going to be not very accurate, especially at the edges, but we don't care because we're just looking for that particular region first. So around the detection, we would do our cropping, um, and then in the cropped image, we no longer need to downsample it at all because this is a cropped image. We'll run our high resolution unit segmentation over here to get the binary output for the wall, and then we also do some post processing to improve the results further over here using morphological functions. So overall, our approach, which is kind of this two-step approach, where we first of all find region of interest and then perform unit segmentation, gave us really high um, dice and IOU compared to, let's say, if you wanted to use unit 256, which would be like this low resolution unit, or even 512 by 512, which is reasonably high unit that could fit in the GPU for us. After that, we basically use a computer vision module where we would identify these two sections separately, and then based on heuristics, we would identify whether the valve is defective or if the valve is a normal valve. We also looked at, to compare our results, we also looked at ResNet and DenseNet in terms of segmentation as well as detection of these faulty valves. So over here, we basically show the attention map of the network, and you can see that it's actually indeed focusing at the right region for its classification for ResNet. So results we got for ResNet and DenseNet as well as FaultNet are over here, right? So the total number of images, as I mentioned, we had was 73. Um, ResNet 50 full over here means that we basically run ResNet on the high resolution image. ResNet crop would mean that we basically run it on this cropped image that is obtained after finding the region of interest. And similarly, DenseNet full and crop refers to the classification of a faulty versus normal wall on the full resolution image as well as the cropped image. Um, while the results are reasonably high for accuracy, that does not tell us the whole story. Remember, I had mentioned that it really depends upon your application whether you want skips or overkills, right? Um, so skip would over here would mean escapes, right? Uh, you do not want a faulty valve to be classified as a non-faulty valve at all. It's okay to have false alarms here and there where you thought it was a faulty wall, but in actuality it wasn't. However, you do not want the opposite situation where you're passing some faulty wall because that can lead to some terrible scenarios. So our method was able to reduce the skips or escapes to zero. So none of the faulty walls were incorrectly classified as non-faulty walls. And we had two overkills, which means that two uh, normal walls were classified as faulty walls. But that's okay. That only increases the manual checking marginally. But this number is, so not only is our accuracy higher, this number is actually the biggest improvement for us. So now let's move on to advanced package interconnects. So just to give a brief introduction, essentially, I'm sure a lot of us have heard of the Moore's law, right? The number of transistors in a given sample area have been increasing consistently for the last 50 years. So and the size of different interconnects that are present in your chips is also reducing significantly with the advancement of technology. So you've gone from C4 soldiers that were 150 micrometers to now most of the work that we did recently was somewhere over here with like 20 micrometer copper pillars. So when the sizes get really small, your yield actually reduces now significantly as well. So while you can package more things in the same area, a lot of it gets faulty now. And to do these detections, you actually need to kind of cross-section the chip and look at what's inside. This is one very expensive. These tools are multi-million dollar tools that need to do this cross-sectioning accurately. It's time consuming and it's destructive technology. You're actually destroying the chip to just analyze whether it's a defective chip or not, right? So normally your package assembly process is traditionally confined to a comfort zone which does not require sophisticated process controls. However, today's advanced packaging performance requirements are forcing the package technology out of this comfort zone or just manually taking a look at it and be okay with the current pace of your model development, with the current pace of of revising your semiconductor chip. um, it's just not enough time to train new engineers to basically look at it in a more leisurely pace. You want something fast paced, you want something that can do it quickly and can do it in an automated sense. And most of these defects that we're looking at are buried inside the structure. That's why we actually need to sort of cross section these data to look at the buried components which are creating some defects in the chip. So the way we do that is using our XRM tools that are present in IME. So these XRM tools are able to sort of, so think of it as your CT scans. Like you can look into your brain, you can look into your heart. Similarly, they can look into the semiconductor chips. So most of this area is your kind of your background area, which can be treated as transparent. What you're looking for are these components inside, which in our data set where there were three components: your TSVs, that stands for through silicon vias, and you have your memory bumps, and you have your logic bumps. So this one over here refers to logic bump because it contains copper pillar, copper pad, and the solder that bonds these two copper pillar and copper pads together. And then you have your logic data that which is over here. Over here you only have copper pillar and the solder. There's no copper pad underneath yet. So as I mentioned, this part is very time consuming. It is prone to human errors because you need to do manual 3D measurements. To do this kind of characterization is very time consuming. So there's a real need for automated 3D metrology. And now the semiconductor industry is feeling its impact of deep learning and computer vision over here. So and slowly moving towards AI-based automation. In the whole process, there's lots of integral steps that need to be done. You need to fabricate the data that includes these defects. You need to do data collection. Like after fabricating, you have to measure, you have to perform these 3D scans. Once you obtain the 3D scans, you have to manually annotate the data in 3D, which is exponentially harder to do than doing it in 2D. Then you have to train your models, and then you have to do your data analysis. And eventually, the goal is that for components like these, we can do segmentation both 2D as well as in 3D. So yeah, process engineers can look at this along with automated measurements of different components that are present in each of these regions, as well as whether we think there's a defect or not, if we found a crack somewhere or not. This kind of information will really go a long way in helping the process engineers in semiconductor fields. So as I mentioned, there are three different components. We had TSVs, through silicon vias, logic die, and memory die. Some of the major defects that we were looking for were voids that are present in these are essentially air pockets. So your solder is basically something that binds two components together, like over here. And sometimes what happens is that due to certain parameters, machine parameters or temperature, pressure, uh, it will induce some kind of air pockets inside, which is really bad for the chip, and this will cause the chip to malfunction. And this can happen in all of these three different mm, components, and there can be more than one void, as you can see over here. So uh, we basically fabricated the data ourselves. In a sense, our sister institution IME did that, where we purposely created defects um, to to basically manage to, so we can train our models to identify these different segments that are present in 2D and 3D data, and then we compare our results. So this is n chi CNN, essentially is the chi CNN that we talked about before. N means just like an ensemble model, and NN unit, as I've talked about from Fabian, and VNet, which is essentially like your unit 3D, but along with residual connections on top. So these are some of the visual results we obtained using these three different networks, and you can see that it's very close to the ground truth, right? Uh, not much of a difference in terms of the output for VNet and then unit and KCNN, unless you like go into really nitty-gritty details of the fine details, which is very important as well. So these are results for the third component, which is your memory die over here. Similarly, we are able to identify the wide regions as well, denoted in yellow. So the way we did our 3D segmentation is again using our anisotropic convolution neural network. The patch size that we used was 19 by 128 by 128 because we perform object detection first to identify these regions. So similar to like how we did for wall dataset, over there we used like a low resolution unit followed by a high resolution unit. Over here we actually used the object segmentation, object detection network to identify this region of interest so we can crop it. So the network basically involves 10 residual blocks with anisotropic convolutions, dilated convolutions, and multi-scale predictions. And then it kind of uses like an ensemble network. So basically given a certain component, you have a segmentation network that would identify the foreground region first. Then for each of these foreground regions, you basically run again binary segmentation networks in parallel. One to look for, let's say, the copper pillar over here, one to look for solder, one to look for voids, and if there are any other things you're looking for. And then you can basically merge these binary masks together as a cascaded as a ensemble network. So it is possible that for one voxel it is classified as part of the solder as well as part of the void. So this kind of ensemble will basically vote to see in cases of disagreements, how like what class you want to assign that particular voxel. And not only that, we also do this segmentation in the three different planars. If you remember, we had frontal, sagittal, so all in those three different planes we do this segmentation separately. So for each voxel, for each of these networks over here, we actually have three different votes in terms of whether it's a foreground voxel or a background voxel. Some of the other networks that we used for our comparison, as I mentioned, was VNet, where they had these residual connections, and we had NN unit, which basically looks at a combination of 3D unit variants, but focuses on the heuristic rules, parameters, pre-processing, post-processing, and so on. After we are able to obtain the 3D regions, we can perform 3D metrology. So essentially, given this voxelized data, we can adopt like a slice and fuse approach. So for each of those 2D planes that are present in each voxel, we basically perform data cleaning using morphological functions. We estimate a 2D rectangle for each of those slices, and then eventually we combine them together into a 3D bounding box for each of those objects. So again, I just wanted to show these results before I go into the numerical results. So visually, all most of them look very similar over here. However, over here, if you focus a bit more, your ground truth void detection is basically the void area is over here. And our network is able to detect this void correctly, while VNet and NN unit kind of over identify this void region inside the TSV. For for segmentation in both logic die and memory die, the results are not that different. They look visually very close to each other. So numerically, essentially, we basically use the standard split approach for train val test. Our model weights are tuned on a train dataset. The validation dataset is used for hyperparameter tuning, and the model is evaluated on this test dataset that is never seen by our model for training or validation. I we're not showing all the results over here. However, we just quickly giving a summary of some results for with augmentation and without augmentation for different components. So for TSVs, even visually, our results did stand out, right? Without augmentation, as you can see over here. For solder as well as void, our results are quite close to 1, right, which is the theoretical maximum you can get, and the results were pretty great. However, as we added augmentation, our results actually significantly dropped. And I think this is the part where NN unit basically really works very well because it identifies what augmentations are actually useful for the particular data you're looking for, which just using off-the-shelf rand augmentations and all doesn't really work for you. Like you have to manually figure out what's working, what isn't working for you. These are some of the results for memory die. We had similar results for logic, so I am not putting them over here. But you can see that once you are able to integrate augmentation inside, NN unit is basically doing a great job compared to both VNet and CNN. And the reason is that basically now with augmentations, it's able to not only figure out great hyperparameters, but also what augmentations to use to improve the results even more significantly. So these are results for the automated 3D metrology based on our idea. And the average error we had was basically 2.1 micrometers, which was already lower than what we expected for our baseline methods. This corresponds to about 3 pixels. And in future work, we plan to reduce it further down to less than 2 micrometers, which is a requirement for AME. So now to recap, these are some of the observations we had for 3D segmentation networks based on our experimentation so far on voxelized data. Using a batch size of 8 or more allows us to use batch normalization and take advantage of the batch statistics. However, the problem becomes that due to limited GPU memory, we may have to take a look at a smaller size rather than the entire resolution. So basically, there's pros and cons of using a higher batch size data. Um, we also experimented with sophisticated data augmentation techniques, and as I mentioned, some of them just do not provide additional improvements, and in fact may even lead to reduction in the final die score. We also tried some other papers which talked about using conditional random fields, right? Using post data processing techniques and all. Some of it helped, but most of the times it made results worse. And even on top of that, things like CRFs are very computationally intensive. So just not the right direction in our opinion. Increasing the network depth further didn't improve the performance. However, increasing the network width, which is improving or increasing number of features or filters, consistently improve the results. So if you're not getting great output, um, I would recommend adding more filters in each layer rather than just adding more layers inside your convolution neural network segmentation books. So to overview, um, we basically talked about 2D and 3D segmentations. Modality is very important, whether you're looking at point cloud data, voxelized data, RGB or RGBD data. Use case definitely matters. For 3D, data augmentation, hyperparameter tuning is even more critical. And usually you have to account for data imbalance or especially noisy label data in 3D, along with having very little label data to work with. Thank you for your time. If you have any questions, feel free to email me or we can discuss during our weekly session later this week.